Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad bin Abdul Hamid, matric number 1810823. This is Organic Chemistry course BTEN 2211, and I will be giving a lecture about carbohydrates. So I will give some introduction first. Carbohydrate is one of major classes of organic compound common to living system besides protein, lipid and nucleic acid. Carbohydrate is a very useful biomolecule that made up huge portion of the food we eat every day, and it provides most of the energy we need to live our days. Carbohydrates are very familiar to us eventually, as we call many of them sugar. So, fun fact, sugar is a combination of Sanskrit words su, which means sweet, and gur, which means sand. Thus, its literal meaning is sweet sand. Okay, without further ado, let's go to the first part of this lecture, which is classification of carbohydrates. Another fun fact, the Latin word for sugar is saccharum, and the derived term is saccharide. Okay, take note of this saccharide term, as we will see bunch of them in this topic. Learning about carbohydrates, we can do this. There are few classification of carbohydrate, and to name it, we use Greek word plus saccharide, which I just mentioned just now. So the first one, monosaccharide. Mono means one and saccharide means sugar. It is the simplest form of sugar. The second one is disaccharide. Di means two and saccharide means sugar. It can be further cleaved into two monosaccharides. And the third one is oligosaccharides. Oligo means few and saccharide means sugar. It can yield 3 to 10 monosaccharides units on hydrolysis. And the fourth one is polysaccharide. Poly means many in Greek, and saccharide means sugar. It can yield more than 10 monosaccharide units on hydrolysis. There are over 200 different known monosaccharides, which can be further grouped into two. The first one is polyhydroxyaldehydes, also known as aldoses, and the second one is polyhydroxyketones, also known as ketoses. Okay, take note of these oses here. We'll found many of them after this. Oses denotes the functional group of carbohydrates. So we move to the next part of this lecture, which is Fischer projection and DL notation. Okay. Stereochemistry of carbohydrate was made easy by Fischer projection. Fischer projection is a two-dimensional representation of three-dimensional organic molecule by projection. In easy word, this Fischer projection here appear in two dimension, but we also can know the three-dimensional form directly. How? By its projection orientation. The horizontal line here denotes the wedge, and the vertical line here denotes the dash. And in general form of Fischer projection, the position of the molecule will be carbon chain in vertical with the aldehyde at the top, and the hydroxyl group and one hydrogen at horizontal. There are two enantiomers of glyceraldehyde. What is glyceraldehyde, you might ask? It is a simplest of all chiral aldoses. Like methane for alkane, it is glyceraldehyde for carbohydrate. So for DL notation, how to know which is which is D, which is L? The key here is to look at the OH or the hydroxyl. If it is located at the right if it is D notation. Uh, if it if the OH at the left, it is L notation. So how to remember? Just remember one orientation of OH at the left. It will be the L notation. Uh, and for the other, it will be D notation. So what if there are more than one OH? We will look at the OH farthest from the aldehyde group at the top, or the nearest to the bottom. In this case, we will look at this one, this one, this one, and this one. So remember, just look at the bottom one to determine the DL notation. So let's move to the next part, which is aldotetrosis, aldopentoses, and aldohexoses. So like I mentioned earlier, the class name depend on how many carbon in the carbohydrates. So like this one, it has 3 carbon, 1, 2, 3, and the name is aldotriose, 1, 2, 3, 4, aldotetrosis, 1, 2, 3, 4, 5, aldopentoses, and the last one, 1, 2, 3, 4, 5, 6 is aldohexoses. And just to let you know that every orientation of this monosaccharide has its own name. And these are for the D notation, and if you mirror all of this, it will be the L notation. So for example, you have erythrose, one of the aldoses that have 4 carbon. If you have the OH at the right, uh, it will be called D-erythrose, and if the OH at the left, it will be called L-erythrose. Next, cyclic form of carbohydrate. Furanose is a cyclic form of carbohydrate which have 5 carbon, and pyranose have 6 carbon. Up until now, we've been learning about carbohydrate in straight chain form, but actually, most of the time, carbohydrate will exist in the cyclic form, which are more stable. The straight chain only exists for less than 1%. This feature is the general formation of furanose. By the reaction of carbonyl group at the top and the OH at the bottom, the ring will be formed. So the first step is the chain will curl up like this. If we curl the chain right away, the carbonyl group won't meet the OH but meet the CH2OH instead. So it need to rotate first. Rotate and to be like this. So the connection can happen. And if the ring is already formed, there are two possible products at the outcome. One with the OH at the top and one with the OH at the bottom. These two can be denoted by alpha and beta. If the OH at the top, it will be called beta. If the OH at the bottom, it can be called alpha. So how to remember it? Just remember that B, beta, bird, is at the sky, at the above. And this alpha look like a fish below the water. For pyranose, the formation of the cyclic form will be very much the same. Just the same, the carbonyl group at the top will react with the OH at the bottom, and the orientation, the position need to be rotated so the OH can react directly with the carbonyl group, and as result, We also can get two possible products, the alpha and the beta. In this case, it is D-glucose, so the name will be alpha D-glucopyranose and beta D-glucopyranose. Next, reducing and non-reducing sugar. Reducing sugar is a sugar when the aldehyde and the ketone group is present in the straight chain, while in the ring form is when the anomeric carbon has an OH group attached that can reduce other compounds. What is anomeric carbon? Anomeric carbon is where the double bond O was. And for non-reducing sugar, it is the opposite of the reducing sugar. This is the example for reducing sugar. Okay, this is the aldehyde group, and this is ketone group, and this one is the anomeric carbon, is where the OH is attached, and is where the double bond O was attached to before the ring is formed. Okay, example for non-reducing sugar. Initially, there is an OH group in the monosaccharide. When the disaccharide is formed, there is no more OH group at the anomeric carbon. Also, all monosaccharide is reducing sugar, and disaccharide is non-reducing sugar. Okay, next, disaccharide and polysaccharide. Okay, disaccharides. Literally, the meaning is two sugar, di for two and saccharides for sugar. For technical meaning, carbohydrates that yield two monosaccharides molecule on hydrolysis. The structural is disaccharides are glycosides, in which the alkoxy group attached to the anomeric carbon is a second sugar molecule. Okay, these are the example for disaccharides. We have maltose, the addition of glucose and another glucose. Lactose is when galactose and glucose is mixed together, and sucrose is when glucose and fructose is mixed together. Okay, next, polysaccharides. Okay, cellulose is a famous example for polysaccharides. It is basic components in vegetables and plants. Structurally, cellulose is a polysaccharide composed of several thousand D-glucose units. Okay, and animal like cattle and cow and goats uh, need aid from colonies of microbes to digest cellulose. Okay, the next example is starch. Starch is one direct source of energy. It is a plant way of storing energy. This is the example structure for polysaccharide. Okay, we have reached the end of the lecture. So that's all from me. Thank you very much for listening this this lecture. Assalamualaikum warahmatullahi wabarakatuh.